This timeline shows some of the well-known CNN architectures for vision tasks. So there were some architectures before 2012, but it's really around 2012, or exactly on the year of 2012, with AlexNet, which won the ImageNet Challenge. This one marked the rebirth of deep learning for vision tasks. So this one introduced the ReLU activation functions that we've introduced last week, and the dropout regularization, as well as using GPU training. So these were like game changers for CNNs for vision tasks. And that by 2014, two key models emerged. The VGG-NET, this one emphasized simplicity through repeated small 3x3 filters, right? 3x3. And then they also had the deep architectures, right? And then there was also GoogleNet. So this one introduced the concept of inception modules, right? So these actually combine multiple filter sizes in parallel, okay? So this one improved both efficiency and accuracy. And then in 2015, ResNet architecture changed everything, right, by introducing their residual connections. So this one allowed networks to go extremely deep, right? We're talking about hundreds of layers without suffering from the problem of vanishing gradients that we've talked about last time. So it addresses a major bottleneck in training deep CNNs. And then we have DenseNet. This one extended ResNet's idea by connecting each layer to every other layer in like a feed-forward fashion, right? So this one reduced the number of parameters and improved the feature reuse idea. And so as deep learning moved to mobile and edge devices, architectures like MobileNet and also EfficientNet focused on optimization, right? We wanted architectures that optimize for speed and size. So EfficientNet introduced compound scaling, balancing the width and depth and resolution with also fewer parameters, okay? And then there's also the competition from vision transformers, which we will talk about next. So a convolutional neural network processes input hierarchically, right? At first layer, the filters are randomly initialized and then updated through backpropagation, as we saw, to detect low-level features, right? So we're talking about edges, simple textures, and these are similar to the edge detectors, right? And then as we go deeper in layers, the network starts composing these basic features into increasingly abstract representations. And so the middle layer might respond to things like a wheel or a fur texture, if we're talking about animals. And then deeper layers recognize combinations, right? So entire objects or semantic parts by pulling information spatially and across channels, right? So this hierarchy is what gives CNNs their power, right? So they learn increasingly abstract representations through parameter sharing and locality. So that with that we could reduce the number of weights that are needed compared to a dense network or a fully connected network. So let's walk through the code, and this is an example of layer activation visualization. So here we can understand the purpose of each step as we go deeper in the layers. So in the beginning here, what we do is simply we start by finding the testing image. So here I'm simply using an open source image of a cat, right? And then with that, we are loading the VGG16 pre-trained model. So this one was pre-trained on the ImageNet dataset. And so so we get access to the internal convolutional layers like this, right, from Keras. And so so here we remove the classification. So when you load the VGG16 using this function, as you see here, we printed out the model summary. So this one shows the different blocks that VGG16 consists of. So it consists of 5 blocks of convolutional layers, right? Each followed by a max pooling operation. So we do not have the classification head, which corresponds to ImageNet. So the top where was taken off. And then, so we are using VGGNet, VGG16 here as a feature extractor, right? So what we do here is we first pre-process the data, right? Simple pre-processing operation using the pre-process input function from Keras, right? So this one simply resizes the image to 224 by 224, which is the expected input size for VGG16. So we simply convert it to an array, and then we specify the batch dimension. And then once the image is prepared, so what we do here is we are simply picking the convolutional layers that we want to visualize. So here I picked 2 convolutional layers from each of the 5 blocks, right? So this one allows us to see the progression across depth, right? And we can see and visualize what happens in each block, okay? So once we do that, then we pass the pre-processed image through the activation model, and then we collect the resulting feature map, okay? So then we simply use this plot right here to visualize these activation maps, right? So the result is seen here at the output. So in the first block, in the 2 convolutional layers of the first block, the feature map is detecting things like the edges. It looks like an output of an edge detector, right? So we can see edges, corners, gradients as well, right? So these are the building blocks of vision, right? So these filters light up in many regions, right? Especially along the fur and the outlines of the cat. And then by block 2, right, which we can see here, these 2 convolutional layers, so the activations become more spatially selective, and you may see more distinct textures, for example, fur patterns or facial contours, right? So block 3, also block 4, so we are going deeper, right? So these activations are sparser and fewer regions are highlighted, right? So they likely correspond to things like, so what is more semantically meaningful patterns, right? So like the outline of the cat's body, right? Or the region that contains the cat's face, right? So in block 5, activations here are highly abstract, right? So these filters might activate only in very specific regions, right? So things like the combinations of textures and shapes that the network associates with the concept of a cat, right? So the feature maps in deeper layers of a CNN, particularly as we saw here in block 4 and 5, they're often difficult to interpret visually, right? Because they no longer correspond to a clear edge detector, right? Instead, these activations represent high level, say, conceptual structures, right? So a particular filter in these layers might respond strongly to when it detects things like so patterns that tend to coexist or to co-appear in certain object categories, right? Like say the curve of a tail, right? Or the say the spatial layout of eyes and nose, right? So unlike early layers, as we saw right here, so you can often say that this neuron detects vertical edges or horizontal edges, right? Or it highlights color contrast, right? So later layers detect um, more of the, say, the compositional features that are meaningful only in the context of the task that we're trying to solve, right? Like distinguishing between a cat or a dog, right? So these neurons are not easily tied to a human interpretable patterns, right? But they are very effective at contributing to the network's understanding of what a cat is, right? So with CNNs, we encounter one of the most common criticism, which is that they are black boxes, right? So imagine a CNN classifies a tumor as cancerous or malignant, but how do we know what it based that decision on? Was it um, was it the texture, the size, the shape, right? Some noise, right? So this matters, especially in domains where trust and interpretability are critical, right? So like medical imaging, autonomous driving, and so we can talk about things like GradCam, which is a short for gradient weighted class activation mapping. It's a technique that addresses this challenge. So it shows us where the model is focusing, where the model is looking when it makes a prediction. Okay, so GradCam operates on a simple but powerful principle. So it traces a prediction back to the activations in the final convolutional layer, and it determines their importance by examining the gradient. So let's walk through an example of how GradCam mechanics work. So first we pass the image through the network and then we pick a class score before the softmax layer, right? Say the raw score of the class cat. So then we compute the gradient of that class score with respect to each feature map in the last convolutional layer. So this tells us how sensitive the prediction is to each channel. And then next, we take a global average of these gradients across these spatial dimensions. So these average gradients become the weights, okay? So it's a measure of how important each feature map is to that class. And then finally, we take a weighted combination of the feature maps, multiply each by its importance, and then we sum them up and apply a ReLU activation to keep only the positive signal. And then the result is a class-specific localization map, right? So it's a heat map that shows which regions in the image contributed most to that prediction. Let's take a look at this demo.
So this is a simple demo of a GradCam output using VGG16 CNN. So here we begin by loading VGG16, right? So it is important here to include the classification output, right? And right here, we are simply freezing the model weights. Okay, so we do not want any training to happen during this demo. So we're just gonna do inference or testing, right? So we download an image. So I'm using the same cat image that I used in the previous demo. Okay, and then we simply resize it to 224 by 224, which, as we said, the required input feature for, input size for VGG16. And then we do the same pre-processing steps, okay? And right here, this is the heart of GradCam, right? So we create this sub-model that outputs both the final convolutional feature maps and the prediction score for the target class, right? So using gradient tape, right? So this function right here. So we are simply calculating how much each channel in the last convolutional layer contributed to the final prediction, right? So this is captured by computing the gradient of the class score with respect to each feature map, okay? And then to simply make the heat map interpretable, we simply colorize it using the jet color map, right? So this one. So, and then we resize it to the original image size so we can overlap them on top of each other, and then we blend it with the original image. Okay, so this overlay shows exactly which regions the model used to make its prediction. Okay, so things like the areas with more red or yellow means that these areas contributed the most, right? So then what we do is we finally compute the prediction of the image, okay? And then we generate the corresponding GradCam heat map, okay? So then the result is visualized over the original image, okay? So we can now see in this example so which parts of the image, often things like the cat's face, right? Or the ears, okay, some near the paws here. Um, it also focused on the background, which it shouldn't. So this can be a confounding feature that the model used to make prediction, okay?
So convolutional neural networks have been the cornerstone of computer vision for over a decade, and their strength lies in leveraging spatial hierarchies and exploiting key inductive biases like local connectivity and translation invariance, as we said before. So these biases help CNNs generalize well with relatively small data sets. However, these same design choices limit CNNs in certain ways. So, because they process data locally, typically a few pixels at a time, so this often these CNN often struggle to capture long range dependencies or also what we call global context in an image. For example, relating distant parts of a scene or also understanding abstract object interactions can require more than what CNNs are naturally equipped to handle, right? So these limitations raises an important question. Can we apply models that are inherently designed to process sequences and capture global structure like transformers to vision tasks, right? And the answer is yes. So vision transformers attempt exactly this, right? So they imagine images not as grids of pixels, but as sequences of meaningful visual, say, patches or tokens. So vision transformers were introduced in 2020 by researchers at Google with the paper titled "An Image is Worth 16 by 16 Words." So the central idea is simple. So we treat an image like a sequence of tokens, just like words in a sequence, in a sentence, sorry. So, and then we process them in with a standard transformer architecture. So the first step is to divide the image into fixed size, non-overlapping patches, right? For example, 16 by 16 squares. And then each patch is then flattened into a vector and linearly projected into a high dimensional embedding space. So these vectors are your input tokens. And then to retain the spatial layout of the original image, positional encodings are added to each token, right? So this is important because Unlike CNNs, transformers do not inherently understand spatial relationships. So the transformers pre-process an image into sequence of patches, as we said, and we first prepend a learnable class token to the sequence. So this special token doesn't correspond to any patch. Instead, it's intended to aggregate information across patches through self-attention. So at the end of transformer stack, its final state is used for classification. So each patch vector is augmented with a positional encoding, which helps the model remember and retain spatial information, right? So without these encodings, the model would treat the patches as a bag of tokens with no really structure, okay? So the full sequence is passed through multiple layers of transformer encoder, and each layer consists of multi-head self-attention, and this one allows each patch to attend to every other patch in the image, okay? Also, it consists of layer normalization, which is applied before each block to simply stabilize the training, and also a feed-forward network, which consists of two dense layers with a non-linearity in between applied to each of the tokens. And then we have residual connections, just like in ResNet. So these help preserve information across layers and avoids the problem of vanishing gradients. And so the transformer stack processes all the patches in parallel, and that's the advantage of transformers. So it learns how to combine local and global patterns, right? So at the end, we use the final embedding of the class token to make the final class prediction. If we want to compare the vision transformers with traditional CNNs, so both are designed for imaging inputs, right? But their approach is fundamentally different, right? So CNNs rely on inductive bias. So convolution operations enforce locality, right? So weight sharing, translation invariance, all the things that we've talked about before. So these assumptions help CNNs generalize well, right? Especially when training data is limited, but they can also restrict the flexibility aspect, right? Because CNNs build understanding layer by layer, right? So they start from small local features and slowly they aggregate them, right? Whereas for vision transformers, they make no such assumptions, right? So they view the image as a sequence and rely on attention mechanisms to model relationships between any pair of patches, right, regardless of their distance in the image. So this gives vision transformers a global context, right, but makes them more data hungry, right? They require more training data to learn these relationships from scratch. So in practice, CNNs tend to outperform vision transformers on smaller data sets, but with enough data and compute, vision transformers started to exceed CNN performance, right? That's particularly in some tasks that need some holistic seeing understanding, okay? So as research progresses, we can see an increasing number of studies that try to converge and get the benefits of both worlds, right? So they try to combine CNNs with vision transformers, and those are the hybrid architectures. So these models aim to combine the best of both architectures, right? So the inductive bias and data efficiency of convolutional networks, and the on one side, and on the other side, the long-range flexibility of transformers, right? So there's some architectures like the SWIM transformer, right? This one was introduced in 2021. And it addresses one of the major limitations of standard vision transformers, which is the computational inefficiency, okay, especially with high resolution images. So instead of using global attention, these architectures compute self-attention within local windows. So this idea reduces computational costs dramatically, right? So this one allows communication between windows, and these are shifted between layers, okay? So this one creates an overlap and context flow, right? And this architecture incorporates hierarchical representation, which is similar to CNNs, where spatial resolution decreases with depth. So this makes it naturally suited for some complex vision tasks like object detection and also segmentation. Another example of the hybrid architecture is the ConvNet. So this one reimagines CNNs using design elements from transformers. So it keeps convolution operations at core, but updates everything around it. So it uses GELU activations, layer normalization, and depth-wise convolutions. It also increases the receptive field by using large kernels, okay? So this is inspired by the attention mechanisms global view with vision transformers, right? So the result is a CNN that performs well with vision tasks, right? So with this hybrid approach, we are no longer thinking in terms of CNN versus transformers. So instead, we are combining both of them. So we gain in terms of data efficiency, scalability, and adaptation.